This talk is brought to you by the Bamberg Mathematical Consciousness Science Initiative.
Thank you very much. So can everyone see the slides okay? And hear me okay? Wonderful. Thank you for that wonderful introduction. That's very kind. Like Miria, I'm not pronouncing your name properly. Miria, I'm also interested in how there might be overlaps between what I want to talk about today and your project as a whole, but I'm really pleased from the previous talk that I think there are certainly at least overlaps between the things that we're talking about. Because what I'd really like to talk about is the kind of feeling that there's a difference in mathematics between working on merely consistent theories and really engaging with a realm of objects in some way, and whether someone like me who's a fictionalist about mathematics can make sense of that. So I'm going to try and argue that we can, but there's at least a puzzle there to think about. I've used the terminology of phenomenology partly because it was it was in the invitation. I'm not an expert on Husserl or anything like that, but I think I'm using it in a similar way, in the sense of thinking about what's given to us in experience. So I'm really trying to focus on how it feels, what it feels like to do mathematics and engage in mathematical reasoning, and how that might give rise to puzzles for certain kinds of ways of thinking about the metaphysical nature of mathematics. Before we get into that question of phenomenology, I'd just like to start with kind of an advertisement for being a fictionalist. And one of the main reasons for being fictionalist about mathematics is it's very difficult to make sense of the alternative, I think. So there's a certain sense that when we're doing mathematics, it seems as if we're discovering the properties of independently existing mathematical objects, the objects of our theories. But if we take that seriously and start thinking about what those objects would have to be like if they were to exist, well, they'd have to be mind independent, they'd have to be language independent, they couldn't be spatio-temporal things, they couldn't be acausal. All those negative features tend to get grouped together and given the label abstract. It becomes difficult to see how our normal mathematical methods for doing mathematics, particularly proof from axioms, are such that they're able to tell us anything about objects of that sort. So certainly if we knew that the axioms were true, then proofs would be able to tell us an awful lot of things about the objects that our axioms talk about, because they tell us what follows from the axioms. And if the axioms are true of a domain of objects, then anything that follows from those axioms are going to be true of those things as well. But that just pushes back the problem, right? The problem really is, what reason have we to believe that our mathematical axioms are themselves true of any objects, if these objects are meant to be these mind-independent, language-independent, non-spatio-temporal, acausal things? Our axioms say every natural number has a unique successor. How do we know? How do we know that those axioms are true of any objects at all? Maybe the numbers just stop at some point, or maybe there aren't any natural numbers at all. The difficulty raised by taking mathematical objects seriously is, once we start thinking, well, if they were to exist, they'd have to be independent of us in these various ways, independence of mind, language, acausal, and so on. It's hard to see how we could have any interaction with them to know anything about what they're like. So even though proof from axioms could allow us to work out what follows from what, it wouldn't allow us to know that the axioms themselves are true. So the fictionalist takes this seriously and says, well, look, actually, if we just look at mathematical practice, there's nothing in there that gives us good reason for believing those axioms are true of some independently existing mathematical objects. But that doesn't show that there's anything wrong with mathematical practice. Mathematical practice doesn't require us to know that our axioms are true of any objects at all. And instead, when we think about what we're doing when we're doing mathematics, we should think, well, we're just working out what would be the case if there were any things that satisfied our axioms. So we're telling stories about how things could be as laid out by the axioms, and then working out what would be the case were those stories true. So what the truths are in the stories that are characterized by our axioms. So if we take that kind of perspective, then the worry, oh, how do we know that every number has a unique successor, kind of disappears, right? We don't care whether there are numbers and whether every number has a unique successor, really. When we write down the axioms for arithmetic, we say, I'm going to imagine that there are objects of this sort and then work out what would have to be true if there were such things. So it's part of the content of the story that every number has a unique successor. I no more need to worry about how I know that's true as I have to worry about how I know that Holmes was a detective. I know it simply in virtue of it being what's part of what sets the story I'm trying to tell. So if I know the story, I know that Holmes was a detective. If I know the story of piano arithmetic, I know that every natural number has a unique successor. That's just given in setting up the story, and there's no further thing to be known there. So a view of mathematics as fiction helps to try and dissolve some of these apparent puzzles that mathematical practice doesn't seem to be able to tell us that our axioms are true. Well, that doesn't matter because all we're doing when we're doing mathematics is working out what would be true if there were things of this sort. And that's analogous to kind of telling a story about how things could be rather than committing to this being how things are. Now, we might worry that if maths is just about telling stories, then maths becomes trivial or too easy. But that's certainly not the case, right? Because even once we've settled on what story to tell, the question of what the truths in the story are not completely up to us, right? It's not a matter of anything goes. So in the context of literature, a literary text, the text gives us a starting point for work out what is true in the story, what we ought to imagine as being the case when we engage with the story. But there's other things that are involved there as well. So beyond what's actually written down in the text, at a minimum, we have to take into account consequences of what's said, perhaps the intentions of the author, perhaps common knowledge about what the world's like, and so on. And all of these features place some objective constraints on the question of what the truths in the home stories are, for example. It's not a matter of anything goes or there being nothing right or wrong you could say about Sherlock Holmes. What the truths in the story about Sherlock Holmes are kind of constrained by these features of interpretation. And I like to think of mathematics as kind of a limiting case in this regard. So in literature, there's all kinds of things that we have to take into account in working out what the truths in the story are. But in mathematics, it looks like the truths in the story are just given by the axioms, the bits we write down, and then their logical consequences, right, and not much else. So just as we have the text of a novel and then some logical consequences of that text are going to be part of the truths in the story, and then there's a bunch of other stuff. In the mathematical case, we have the axioms and their logical consequences, and we kind of ignore intentions and all the rest. That doesn't really matter. So the truths in the story of mathematics are given by the axioms and their logical consequences, but even that kind of limiting case example gives us a good deal of objectivity within mathematics already, right? It's not the case that anything goes in arithmetic. Once we've set our axioms, there's going to be facts of the matter about whether there are infinitely many prime numbers and so on. So that's going to give us a good degree of objectivity. But my worry is that it might not give us quite enough, because there is, I think, a sense we have when doing mathematics that there are some sources of objectivity in mathematics that go beyond just this, just there being objective facts of the matter about what follows from our axioms. So we can get a feeling that some axioms are objectively the right ones to have, in that they capture aspects of mathematical reality in a way that other axioms, although they might be consistent, wouldn't do that. So that's one source of objectivity, an objectivity in the choice of axioms. These are the right ones. They capture how things are with mathematical objects. You might think of it that way. That isn't grounded in facts about logical consequence from axioms. So that's one source. And then a second source is, once we've picked our axioms, even if we know that a particular mathematical statement is independent of them, so that neither it nor its negation is a consequence of those axioms, nevertheless, it can sometimes feel as if there's still one objectively correct way of going, one objectively right answer as to whether the statement holds or not. And again, that's a source of objectivity that doesn't look like it's grounded in it being a logical consequence of the axioms. So there's a sense we might have in doing mathematics that the objects of our mathematical theories have a life of their own outside of the constraints of the stories we tell about them. We tell the stories that makes some things the case about the objects, but there's more to them than that. They seem to have properties that are perhaps independent of the stories, or that we can distinguish between the objects that are merely objects of stories and objects that are more objectively real in the first case. So let's explore this phenomenon a bit more. So if you're a fictionalist and you think the maths is simply a matter of working out what follows from our axioms, how does that fit with the feeling we sometimes have that when we choose axioms, we're constrained by something more than mere consistency? So, for example, in the history of mathematics, when mathematicians introduced the imaginary square root of -1, it feels like there was a period in the history of mathematics where mathematicians didn't take that very seriously. They thought of this as a kind of merely formal game, but there isn't really such a thing. And there was some resistance to talking about the square root of -1. And eventually mathematicians came to believe this was perfectly good mathematics. That belief seemed to not track beliefs about consistency. People believed it was consistent all along, but there was a shift between taking it as a merely consistent story that isn't real mathematics to taking it as a theory about a genuine part of the mathematical realm. Leibniz talks about the imaginary numbers having this amphibian status between being and non-being. And if you kind of look at the history of people's thinking about the square root of -1, it always feels like it started in the water of imaginariness and then came out into the fresh air of realness, right? That it eventually gets treated as just as real as any other number. So it seems that there's a shift in the history of mathematics from thinking about these as merely consistent, perhaps useful fictions, to thinking about them as genuinely real numbers, parts of mathematical reality. And that shift, that feeling that there's a difference here in our engagement with imaginary numbers, looks like it's going to be difficult for a fictionalist to make sense of, right? If all we're doing when we're doing mathematics is telling stories and the axioms define what the stories we have, so long as we've got a consistent story according to which there are imaginary numbers, what else is there? What stops us from treating that as perfectly good mathematics? So that's one puzzle for the fictionist, I think, to make sense of. A second puzzle, so that's a puzzle around kind of picking new axioms, and at what point we say that those new axioms really describe realities. But even once we've got a collection of axioms that we're happy with, there's lots of cases where we might want to say that there are truths about the objects that those axioms concern that are not logical consequences of those axioms. So Gödel showed us that insofar as our mathematical theories are consistent and so long as they're powerful enough, they're going to be subject to the phenomenon of incompleteness. So if you've got any axioms for arithmetic in the proof system for arithmetic, there'll be a sentence in the language of arithmetic G that says of itself, there's no proof of me. On pain of inconsistency, neither G nor its negation will be provable. So in that sense, our theory of arithmetic will be incomplete. But nevertheless, it's really natural for us to think that G is true. G is unprovable, and it says of itself it's unprovable. How else could it be? If we think the truths of arithmetic are just what follows from the axioms in the sense of being derivable from the axioms, then it's kind of hard for a fictionist to make sense of our feeling that no, G is really a true sentence, right? Now we might think there's some obvious ways that our fictionists can deal with this. So it's certainly not the case that the fictionist has to rely on a notion of logical consequences grounded in derivability or provability. So they might adopt a semantic rather than syntactic notion of logical consequence. So it might be that there are things that are genuine logical consequences in the sense of they would have to be true if the axioms were true, but aren't derivable from those axioms. That's going to be the case if they adopt second order logic in formulating their axioms. If they adopt first order logic, then truth and provability, semantic and syntactic consequence hang together. But if they adopt second order logic, they can say, well, when I'm talking about the truths in the story of arithmetic, what I mean is what follows logically from the second order axioms for arithmetic. And then they can say, well, G follows from those axioms, even though it's unprovable. But that really, well, we'll come back to that question of whether we can do that trick of using second order logic to pin down the logical consequences of our axioms. But even if we did do that, it still looks like there's a bit of a problem for the fictionalist, because it looks like if mathematics is just a matter of writing down theories and working out their consequences, then it looks like a fictionist should say, take a first order theory of arithmetic that includes the piano axioms and the negation of G. That's going to be a consistent theory, and it's going to have the negation of G as a consequence of that theory. If mathematical stories are just stories we're free to tell, if all that we care about is, in Husserl's words, pure analysis of non-contradiction, that's fine. We can analyze that theory and work out what's true in that theory, and yet we might think that there's something defective about those first order theories that have the negated Gödel sentence in. So there's still, I think, some job for the fictionist in explaining why we think that that's not an appropriate, or why we might think that that's not an appropriate mathematical theory to pursue. Once we move to set theory, it becomes a little bit more complicated again. So in set theory 2, there are open questions. There's a famous example is Cantor's continuum hypothesis that says that the size of the continuum, the size of the set of real numbers, is the next highest infinite set after the size of the natural numbers. That's not answered by the standard axioms for set theory, and it's independent of those axioms. And there's kind of disagreement amongst set theorists as to what we should say about the continuum hypothesis, whether we should say it has a truth value or it doesn't. If you're a fictionalist, it looks like it's hard to make sense of that disagreement from the get-go, because it looks like we should think, well, the axioms tell the story, neither CH nor its negation follows from the axioms, so we're free to tell the story with it being true and free to tell the story of it being false, or multiple different ways of it being false, and all those are equally mathematically good. So the fact that some mathematicians want to say, no, it has a truth value, looks like it might be difficult for a fictionist to make sense of. Now, they might be able to make the same kind of move that they made in the natural numbers case, in the piano arithmetic case, because if we move to second order ZFC, then we have a result of quasi-categoricity, which says that all standard models of second order ZFC will agree about the truth value of, that should say CH, the truth value of the continuum hypothesis. So they'll all either say it's true or say it's false, we just don't know which. However, we might feel a bit queasy about this move in the set theory case, because it itself is a result within set theory, and our choice of which background set theory to use to develop that result will make a difference to what truth value the continuum hypothesis has in all models of the sets, right? So if we choose a background set theory with the continuum hypothesis as false, it's going to give one answer, and if we choose a background set theory with it as true, it's going to have a different answer. So to say that it's answered by second order logic, given that the questions of what the models of second order set theory are themselves set theoretic questions, you might think that's not really going to settle the answer. So if we do think that there's a fact of the matter about the continuum hypothesis, it's unclear that the quasi-categoricity proofs are going to be useful as a ground for explaining that. And if we can't rely on those proofs of categoricity to convince ourselves that there's a fact of the matter about the continuum hypothesis, we might worry about relying on them to support our belief in the Gödel sentence G, right? Because if there's dispute over what the second order, what models to use in modeling the second order consequence relation are, then saying that it's got an answer in second order logic isn't really going to help us. So if we and finally, even if we did think that the second order move helps us in the set theory case as well, we'd still have that further question to ask, well, what would be wrong with the consistent first order stories we could tell that offer different answers to the continuum hypothesis? If mathematics is just pure analysis of non-contradiction, all of those count as perfectly good bits of mathematics as well, right? So it doesn't look like there's an easy answer to what's wrong with these stories. But we might at least think in the set theory case that an option would be available for us to say, actually, there's nothing wrong with any of those alternative stories. Each of them are perfectly good bits of mathematics, right? We could say there's set theory of the continuum hypothesis and set theory with various ways of negating the continuum hypothesis, and all of those are equally good. And that's certainly the approach that some set theoreticians take, right? Some set theoreticians say that the lesson of the independence of the continuum hypothesis is that we don't have a single universe of sets, we have a multiverse of equally good set theories with all of which tell different stories about what the answer to the continuum hypothesis is. And we might think this, if that turns out to be the lesson of the continuum hypothesis, then at least in the set theory case, this is good news for the fictionalist, because it looks like it's grist to the fictionalist mill, right? All of these equally consistent stories are good enough. None of them is more real than any other. But really interesting to me is that one of the main defenders of this kind of multiverse picture of set theory says that actually that's when we think about the way that mathematicians engage with this multiverse of set theory, actually it supports a kind of more robust realism about these different worlds, right? We shouldn't think of them as merely consistent stories, mere stories we could tell about how the sets could be. Our experience of them is as of universes just like any other mathematical universe. So Hampkins thinks about, he presents an argument against people who think there's only one real universe of sets that comes from the phenomenology of set theoretic practice within the multiverse. So the single universe view says there's some particular answers to the continuum hypothesis. That's how the sets really are, and then any other theory that gives a different answer to the continuum hypothesis, it might be consistent, but it's not really getting things right about the sets. Hampkins says, well, if you think about our experience of working within these multiple realms in set theory, this presents a challenge for the single universe view. Because someone who thinks that there's a single absolute background concept of set is going to have to explain away as imaginary all these alternative universes that set theorists seem to have constructed. And that seems a difficult task because we have a robust experience in those worlds. They appear to us to be fully set theoretic. Whereas on the multiverse view, we explain that experience by embracing them as being real. filling out the vision hinted at in our mathematical experience, that there's an abundance of set theoretical worlds into which our mathematical tools have allowed us to glimpse. So Hampkins, rather than taking the kind of multiverse picture in set theory as showing that they're all equally, they're all just stories we could tell, they're all kind of imaginary. He wants to say, no, our experience of working with these is experience of working with in fully real realities. It doesn't feel like these are imaginary, merely consistent imaginary alternatives. So we should really think that there really exist all of the objects that our alternative set theories describe. And Hampkins tells a kind of interesting story about the history of the development of multiverse set theory as analogous with the history of developing alternative geometries, which seems to suggest a shift between a point where we think of these as merely consistent stories to a point where we think, no, these are real now. That again is hard to make sense of from a kind of fictionist perspective, it looks like. So Hampkins says there's a very strong analogy between the multiverse view in set theory and the most commonly held views about the nature of geometry. So for 2,000 years, mathematicians studied geometry, proving theorems about making constructions in what seemed to be a unique background geometric universe, the Euclidean one. In the late 19th century, however, geometries were shocked to discover non-Euclidean geometries. At first, these alternative geometries were presented merely as simulations within Euclidean geometry, a kind of playful or temporary reinterpretation of the basic geometric concept. So, but through that simulating these geometries within the Euclidean world, you could see that they're consistent, but they're not real, right? They're not real ways that space could be. By temporarily regarding line to mean a great circle on a unit sphere, one arrives at spherical geometry where all lines intersect. By regarding line to mean a circle perpendicular to the unit circle, one arrives at hyperbolic geometries where there's many parallels to a given line through a given point. At first, they were considered as curiosities, useful perhaps for independence results. They're kind of logically helpful, but for with them, one can prove that the parallel postulate is not provable from the other axioms. But in time, geometers gained experience in the alternative geometries, developing intuitions about what it is like to live in them. And gradually they accepted the alternatives as geometrically meaningful. Today, geometers have a deep understanding of the alternative geometries, which are regarded as fully real and geometrical. So Hampkins describes that kind of phenomenological shift between working within the geometries as kind of toy models where they're not taken seriously as ways that space could be, to seeing them as genuine geometries, genuine descriptions of mathematical spaces. And he says the same happens in set theory, right? We start working in set theories with different answers to the continuum hypothesis. We think, well, there's one true answer, but let's see what would be the case in this. We see that it's consistent and so on, and we find a submodel of the universe V of sets in which it's true. So we can say, okay, well, we can prove consistency this way, but eventually mathematicians start engaging with these as set theories in their own right. That phenomenological shift looks hard to make sense of if we think, well, all we're doing is telling stories, all we care about is mere non-contradiction and the analysis of what follows from non-contradictory axioms. So I hope to have convinced you that there's at least a couple of tricky features for a fictionist to make sense of from the phenomenology described so far. It does seem we distinguish between merely consistent theories and genuine mathematical realities. So in the case for arithmetic, where there is a good degree of consensus that the alternative consistent first order theories of arithmetic are in some way defective, we distinguish between the merely consistent theories of arithmetic and the true theory about the natural numbers. On the other hand, in the case of set theory, where there's not this consensus that the alternative set theories are defective, we might think that this is grist to the fictionist mill, but actually Hampkins' suggestion that even there's this phenomenological shift between the case where we think of them as merely consistent theories and thinking of them as genuinely alternative ways sets could be, is also tricky from a perspective which says that we're just telling stories defined by axioms. So in both directions, it looks like there's a pressure to think of a difference between merely consistent theories and the genuinely true ones, the ways that mathematical objects could really be. So the question I have is there a way of making sense of this difference if you're a fictionist about mathematics? Well, I think there is, and I think the difference can be made sense of if we go back to that analogy with fiction and kind of lean into that a little bit more. So the question is, if these are mere stories, how can we make sense of the idea that some stories get some things right about the objective mathematical world where others don't? If we think about the analogy with literary fiction, actually not all fictions are equal when we think about engaging with them. So authors of fictions don't just tell any story they like, they strive for, so looking at, this isn't, there's not much philosophical literature on this, but looking at kind of fiction writers talking about the principles of writing fiction, people talk about verisimilitude in this case, but by which they mean believability. And that's not to say that fictions have to be believable in the sense that, you know, we can't have very, very different scenarios from the actual world. We're very happy to suspend our disbelief and engage with fictions that are very far from the truth, but there are, it seems, some limits to that, particularly with characters. If we find it really hard to imagine a real person behaving the way described in the fiction, then we're less likely to find the fiction believable and engage with it. So there's amongst all the consistent stories we could tell, we find some engage the imagination in a way that others don't. We can't really make sense of this story because we can't really imagine someone behaving that way, for example. And I think a limiting case of this is discussed in the philosophical literature. It's what's called imaginative resistance. Cases where people engaging with a fiction either can't or won't imagine the scenarios described by the author. So in the literature, this is often involved cases where we have situations involving moral evaluations that differ from how people would. So if someone's described as behaving as a particular way and it was good, people will resist that in a way that they won't resist perhaps other counterfactual or even counterpossible imaginings in fiction. So we do have limits on what we take to be acceptable in the story based on what we're willing to imagine. And I think this feature of imaginative engagement can help to explain this feeling that some mathematical stories really are better than others. So if we think about the case of arithmetic and those non-standard stories about the mathematical, about the numbers that say that G is false. Effectively, those stories require non-standard models, right? They require, in order for those to be, any world in which they'd be true is a world where the numbers are not laid out the way we think numbers should be laid out, as a first and the next and the next and the next and so on and nothing else, right? But when we're thinking about what it would be like to be the natural numbers, I think our thinking is tied to our grasp of how numbers could be, how counting numbers could be, which is tied to this structure of a first and the next and the next, this kind of the Kantian idea of arithmetic as being grounded in temporal succession. So if someone asks us to think about numbers that fail to be in that kind of way, it's not surprising, I think, that those mathematical stories meet with imaginative resistance. Maybe they're consistent stories, but we can't imagine the numbers being that way because the numbers are meant to have this structure to them. So it's not going to be surprising that we find that even though these stories are consistent, we won't engage imaginatively with them because it's part of our picture of what numbers ought to be like, that they have this kind of structure that's not allowed in these models. So that's the case of the natural numbers where we do kind of resist treating these alternative models as real. But what about the second case, the Hampkins case, where we shift from treating theories as merely formally consistent stories to thinking of them as genuine accounts of how space could be? Here, I think, again, we can understand this in terms of imaginability. We couldn't imagine the parallel postulate failing, it was unimaginable to us because we had in mind that geometry describes Euclidean structures, right up until it wasn't unimaginable. It became imaginable to us that there could be spaces that where the parallel postulate changes, because our imaginative capacities developed through thinking about these alternative models of geometry. So again, I think it's not surprising that there might be a phenomenological shift from thinking of these alternative geometries as just merely consistent sets of sentences that we're manipulating to work out their consequences, to thinking of them describing genuine ways that things could be. And plausibly, the same kind of move can happen in the development of set theory. Mathematicians get so used to thinking or working in the alternative set theories that they start to be able to imagine them as ways that sets could be, and think of themselves as finding glimpses into a new reality. That shift can happen, but we needn't think of it as evidence of the reality of the multiverse as opposed to evidence of our imaginative capacities improving, right? We've being able to now see these, what were purely formal descriptions, as descriptions of a way the world could be. And interestingly, so going back to the case of standard models of the natural numbers, Hampkins thinks that we might have this kind of development even in the natural number case as well. Because he thinks, insofar as we get used to working with these different universes of sets and different concepts of sets, we will get used to the thought that there could be different accounts of what the possible subsets of the natural numbers are. And then find it natural to think that there are actually different answers to the independent questions in arithmetic as well. So although it might seem that saying 1, 2, 3 and so on has to do only with a highly absolute concept of finite number, the fact that the structure of the finite numbers is uniquely determined depends on our much murkier understanding of which subsets of the natural numbers exist. So why are mathematicians so confident that there's an absolute concept of finite natural number, independent of any set theoretic concerns, when all of our categoricity arguments are explicitly set theoretic and require one to commit to a background concept of set? My long-term expectation is that technical developments will eventually arise that provide a forcing analogue for arithmetic, allowing us to modify diverse models of arithmetic in a fundamental and flexible way, just as we now modify models of set theory by forcing. And this development will challenge our confidence in the uniqueness of the natural number structure, just as set theoretic forcing has challenged our confidence in the unique absolute set theoretic universe. So Hampkins thinks we might become convinced of a multitude of natural number structures corresponding to all the consistent first order theories of piano arithmetic, in the same way that we can become convinced in a multitude of set theoretic structures. And this would convince us, the upshot of that would be that we'd be realists about these alternative numbers and so on. Here I want to say the same phenomena could be equally well explained by thinking that experience in thinking about alternative set theories has expanded our imaginative capacities in such a way that we no longer think that ways numbers have to be grounded in that temporal succession. Okay, so just to sum up then, it does seem that there's this phenomenological distinction in mathematics between merely consistent formal theories and theories that describe a genuine way that mathematical objects could be. And on the face of it, that presents a challenge to fictionalism, because it's hard to see, if we don't think that our axioms ever truly describe any objects, then it's hard to see how we can choose between one bunch of axioms and another, or choose between one independent claim that doesn't follow from our axioms as opposed to another one. I've suggested, however, that the phenomenological distinction we find can be understood through thinking about imaginative engagement. So even though all mathematical fictions all consistent fictions are in some sense good enough, only some of them will engage our imagination in a way that we we will think of them as genuinely describing a way that mathematical objects could be. But this distinction isn't going to be evidence for a realm of mathematical objects. It's going to be an evidence of the role of imaginative capacity in our engagement with mathematical theories. And I'll stop there. Thank you.